The project that I developed encompassed the quadruped robot that we evolved during class. The initial desired goal of the quadruped was to visualize the closest object to its body using proximity sensor raycasts. I was able to develop a neural network that allowed for the evolution of a robot that navigated a course randomly, finding any object at any given time, but found it very hard to satisfy the requirement of finding the closest object without strictly forcing the robot to find that object. The video that is currently playing shows one of the best evolved robots that is randomly navigating a course of objects during a given time frame. The fitness function is merely represented by the number of collisions detected. The neural network utilizes a binary representation of the collisions of the raycasts at any given time and uses the detected collision from a ray to find the relative coordinate location and the Euclidean distance from the object. These values are added together and then multiplied by the 32 synapses that are the weights for the joints and sensors of the robot initially. I decided that I wanted to take a step further and chose to attempt to minimize the time during a collision as well as maximize the number of collisions of the robot with an object. Most of the fitness curves shown symbolize the specific evolution of minimization of the time between collisions. I noticed that the evolutionary algorithm attempted to minimize the time and disregard the number of collisions and called that the most efficient traversal. If I had more time, I would investigate more constraints to hold both fitness functions too. I believe that if I were able to both maximize the number of collisions and minimize the length of time between any two collisions, then the robot will eventually try to find the shortest path to any given object.